So chapter 11 is about coupled oscillators in normal modes. So what we're going to be doing here is looking at when you have, we're going to use a model of something like when you have two masses connected on a spring to each other and also to other springs. And this is going to seem fairly canned at first because you don't come up with this scenario very often in the real world. But this is a good approximation because remember that life is just a mass on a spring. So this is a very good approximation of other situations, such as when you have molecules, atoms inside of molecules, you can, to a good approximation, treat them as coupled masses coupled through springs. And then, and of course, if you want to solve this more precisely, you have to use a quantum mechanical solution, but a classical solution is still a pretty good approximation, and you can also use it for other problems where you have multiple objects connected with each other. So you can use this for acoustics, bridges, buildings, and also coupled electric circuits. So we're going to start with, we'll show you how to do it in the case of two masses coupled with three springs, but then we're going to expand this more generally. We won't solve the math of it, but you could have multiple, you can have higher and higher order equations, and we're going to solve this problem with matrices. So we'll limit the order of the matrices that we're using in this chapter to approximately 2. I might sneak in a little bit higher, but the approach can be generalized. So we start with two carts. We will treat them as moving on a frictionless surface. We have M1, M2, and they are connected to the walls and each other with springs. And we will call our springs, we will say our springs have spring constants K1, K2, and K3. And this is figure 11.1. So we can go about deriving the equations for this in two different ways. You can either use Newton's laws and get the force equations that way, or you can use the Lagrangian and get the force that way. So if we consider the force on the first mass, we are going to define the positions. So x1 is in this direction, and it is the displacement from equilibrium. And x2 is in this direction, and it is the displacement of the second mass up. I'm a little bit off scale here. So x1 is the displacement of the first mass from equilibrium, and x2 is the displacement of the second mass from equilibrium. We'll put it here. And then the force on 1, actually we will not, it's all in one dimension, so we're going to drop the vector sign and just look at the magnitude. And this is negative K1 x1, so that it is, if x1 is positive, the displacement is in that direction, just from the first spring. Plus, and then K2 x2 minus x1. So if this is crunched or extended, then there is a restoring force to pull this spring back to its equilibrium position. And we can rewrite this as, we're going to group the x1s and the x2s, negative K1 plus K2 times X1 plus K2 X2. And we can write the force on the second mass. And this is all equal to M1 X1 double dot. So we can write the force on the second mass then as negative K3 X3 plus K2 X1 minus X2. And this is M2 X2 double dot. And we can rewrite, actually I'm going to rewrite that in the same form here as K2 X1, so my X1s are first, minus K2 plus K3 X2. Now, if I want to write the Lagrangian is 1/2 M1 X1 dot squared plus 1/2 M2 X2 dot squared minus 1/2, and then I have K1 X1 squared plus K3 X2 squared, that's just these two, plus K2 X1 minus X2 quantity squared. And then I can do partial L, partial X1 is negative K1 X1 minus K2 X1 minus X2. And this is equal to partial L ddt partial L partial X1 dot, which is just M1 X1 double dot. Partial L partial X2 equals negative K3 X1 minus K2 X2 minus X1, which is equal to d dt partial L partial X1 dot, or sorry, X2 dot, which is M2 X2 double dot. So this term, so if we look at the X1 equation, that gives me this term, and this term I just flip the sign, and then the X2 equation is this term, and then here this term, again I just flip the sign and I get the same terms. So either way I get it, I get the same answer. And now I'm going to take these two equations, and I didn't put here, I want M2 X2 double dot. I'm going to write this as a matrix equation. So matrix equations are really just a way of noting multiple equations at the same time, multiple linear equations. So here I have M1, 0, 0, M2 times X1 double dot, X2 double dot equals negative, I dropped a negative, no, I don't want a negative sign there. Negative K1 plus K2, K2 plus K3, negative K2, negative K2. I put the negative sign out, and it will become clear in a minute why I put that negative sign there, times X1, X2. So I can write this as the matrix M times the vector X double dot equals the matrix K times the vector X, where this is M, this is X double dot, this is X, and this is K. So I have now written my problem as a matrix equation, and I dropped a negative sign, and this actually looks stunningly similar to our equation for simple harmonic oscillation. M X double dot plus K X equals 0. So we're going to find that this has equations that are similar to that, except each of the individual components is itself an oscillation. Okay, so I have moved the matrices up there and just taking quick notes on what they are. What we're going to do is try a test solution. And there's a few different ways that we could write this. They're all more or less, many of them are more or less equivalent. We can write X1 is alpha cosine omega t minus delta 1, some phase shift. X2 is alpha cosine omega t minus delta 2, some other phase shift. In general, they can be different, but it's usually easier to use complex numbers because it's easier to take the derivative of an exponent. So we will use Z1 equals A1 e to the I omega t. Z2 equals A2 e to the I omega t. And X equals the real part of Z. So then Z dot is I times Z. When we take the derivative, we just get a factor of I because it's in the exponent. Z double dot is then I squared Z, which is equal to negative Z. So then if we want, we could write Z is, let me move this a little bit. I am using Z is Z1, Z2, which is the vector A, e to the I omega t, where A is alpha 1, alpha 2, e to the negative I delta 1, e to the negative I delta 2, and I make a vector out of it. So I am simply, so that is how I connect this z to the x's there, because if I take the real parts of that, I am left with x1 being alpha, this should actually be a 1, alpha 1 cosine omega t minus delta, and x2 is alpha 2 cosine omega t minus delta. All right, so we're going to plug our solution into our equation. And this may look familiar. What we're going to do is actually an eigenvalue problem. A lot of physics problems come down to eigenvalue problems. So since z double dot is equal to negative z, x double dot is equal to negative x, and we will rearrange, z double dot, I missed something big here. This should have an omega when I take the derivative. I'm a little distracted today. It's been a very busy day. It's been a very busy week. I have an omega squared here. So then I plug this in and I get m omega squared. I'm going to put everything on one side, minus k, all acting on the vector x, equals 0. So this is the equation that I want to solve to figure out how to solve this problem. So this is actually, so we've assumed a certain form of the solution. If we can solve this for the omega, we can find all general solutions. So what we're going to do is take the determinant of this matrix, solve it for omega. That will give us the allowed omegas. And then for each of the allowed omegas, we will have a vector x, which is allowed, which corresponds to a vector a, those little coefficients. So, and then we'll once we have the omega, we're going to plug that back in, and we will find out what the A's are that way. That's going to give us a general solution for all allowed solutions of x, and we then have an initial value problem. So this is just like what you saw when you had differential equations, but now it's in multiple dimensions because we've got coupled oscillators. All right, so now we're going to consider a special case. We're going to consider two equal masses. So that makes our m 0, 0, m. And we're going to consider the springs all having the same spring constant too. So then this becomes 2k, negative k, 2k. And then k minus omega squared m is equal to 2k minus omega squared m along the diagonal. Somehow I still manage to make typos even when I'm writing. And then when we take the determinant of that, we get 2k minus omega squared m, quantity squared, minus k squared, and this is equal to 0. So we can solve this for omega squared. I'm going to put the k on this side. And then I can take the square root. So this is the k. So this is k squared. And then I take the square root and I get a plus or minus. And then I'm going to divide through by m. So here I am, and then I can solve this for omega squared. Omega squared equals 2k over m minus plus k over m. So my two solutions are either 3k over m or k over m. And you will notice that this one looks like if we had just one mass oscillating on one spring. We will call this omega naught squared. All right, and then we are going to first look at the solution for this one. So omega squared equals k over m. So we're going to plug that back in here, and that gives us, so here, I did it in a slightly different, so now I have k, and I'm going to put ka equals ma. So now, ma omega squared. So my k is 2k, negative k, 2k, and then I have a1, a2, and that is equal to omega squared times m. Now omega squared is k over m, so this becomes, omega squared m becomes k, 0, 0, a1, a2, and then I can convert this into equations. Now what you will see is that there's always a duplicate equation. So in a problem with a 2 by 2 matrix, one of the equations is it can be written as the other one. In a 3 by 3 matrix, one of the equations can be written as a sum of the other two. All right, so then here I have 2k a1 minus k a2 equals k a1. So I can move this guy here, move that guy there, and cancel out the k's. And I get a1 equals a2. And this actually should be a k. I had a typo right there. Okay, so I get a1 equals a2. I kind of prefer normalized vectors, so I'm going to write my a1 as 1 over the square root of 2, 1, 1. And what this tells you is that when you have something oscillating with the frequency square root of k over m, then both masses are moving together because x1 and x2 are both proportional to cosine omega t with the same phase shift. So your masses are doing this. That's your first mode. And the reason why that has the same angular frequency is because this spring, it's the same thing as if they were oscillating completely independently. The middle spring is never stretched. Now we can look at omega squared equals 3k over m. And when we do that, this is the same. And now I have, now I have a 3k, a1, a2. And when I convert this into an equation, I have 2ka1 minus ka2 equals 3ka1. And now I'm going to move this to this side, and I can cancel out the k's again. And I am left with A1 equals negative A2. And that would give me an A of 1 over the square root of 2. That's just because I like normalized vectors. You actually don't have to do it, but it will change the constant out in front. So here, what this is doing is that the springs are oscillating relative to each other. And then when that happens, the middle spring is stretched at the same time that the other two are compressed, so it changes the oscillation frequency. All right, so then we can clean this up a bit, and I will write out the equation for the general solution. All right, so we have two solutions. So we can, in general, write our solution x as some constant, C1, times, I guess I'll wrap that constant out in front, the first mode, cosine, the square root of k over m, t, minus some phase shift, plus some constant for this out in front of the second term, cosine square root of 3k over m, t, minus some other phase shift, which does not in general have to be the same. So all of your solutions can be written right like this. And in this particular case, because the oscillation frequencies, omega 1 is, or omega 2 is the square root of 3 times omega 1, there is no time when this system will start repeating itself. It is not periodic, but because there's no multiple, it's never a multiple of 2 pi of the other oscillation frequency. So you won't get repeating motion, but you can describe then motion in all time like this, as the sum of the two carts moving together, and the two carts oscillating like this, exactly out of phase. All right, so we chose to use the coordinates x1 and x2 as drawn, the displacements of the two masses from equilibrium. But we don't have to make that choice. We could choose to use a different set of variables. So we could have chosen C1, which is 1/2 x1 plus x2, and C2, which is 1/2 x1 minus x2. And if we did that, then we could write our solution as, let me call this A1, C1, cosine square root of k over m, t minus delta 1, plus A2, C2, cosine of the square root of k over m, t, minus delta 2. And this guy is just 1, 0. And this guy is just 0, 1. So so if you choose this basis, instead of using x1 and x2, you use this basis, c1 and c2, then you have a much simpler equation. You are describing all of the motion as the sum of either moving together or move exactly in phase, or moving apart exactly out of phase. And those of you who've taken a linear algebra class will recognize that this is in fact just a translation of the of x1 into x2. So we can write C equals some matrix times x, times anything, C is some matrix times x. In this case, it is, there's a 1/2 out in front, and if I want to get C, I'm going to multiply, there's a 1/2 out in front, there's a 1, 1, and C2 becomes -1, 1. So this is simply a rotation of our basis vectors. We're going from using x1 and x2 to using a different basis. And we sometimes call C1 and C2 normal coordinates. They are in fact the natural coordinates to describe the system. And then each of our oscillations varies independently. So if we choose the right coordinates, you can describe the system in a much simpler way. The math gets a lot easier. Now, after you've done a few of these, you might be able to guess the right way to solve the problem. Often there's some solution where things are moving together and some solution where they're moving apart. But in general, no, I'm not good at that. If I'm not good at it, I don't expect you to be either. So we use the techniques that we use in linear algebra in order to find these basis vectors. So now I'm going to solve this in a more general case. And mark here, I can't go there. So we will write k minus omega squared m is k1 plus k2 minus omega squared m, k1 plus k2 minus omega squared m, negative k2, negative k2. The book approaches this for the case that k2 is much smaller than k1. I'm going to solve it in general because it's actually not that hard. K minus omega squared m. The determinant of that is k1 plus k2 minus omega squared m quantity squared minus k2 squared, and that is equal to 0. So we get k1 plus k2 minus omega squared m is equal to plus or minus k2. I am going to divide through by m. And then I'm going to put this on this side and this on this side. So I get omega squared is equal to k1 over m and then plus k2 over m plus or minus k2 over m. So omega squared is either k1 over m or k1 over m plus 2 K2 over M. And we're going to, we will look at K minus omega squared M acting on the vector A. And our first equation is K1 plus K2 minus omega squared M times A1 equals K2 times A2. I'm going to be lazy. Remember, a good physicist is a lazy physicist. And I'm not going to come up with the second equation because I already know that it's redundant. You can actually see that it's redundant. I will leave that as an exercise for the student. So then we will first consider omega squared equals K1 over M. And in that case, I get K1 plus K2 minus K1 A1 equals K2 A1. So these guys cancel, and I get, this is an A2, I get A1 equals A2, which corresponds to A is 1, 1. So this is the mode where the two masses move in phase together. Okay, so then we're going to look at the second one. Omega squared equals K1 plus 2K2 over M. And we will evaluate this equation, and I'm just going to look at the top row, so the first equation. I get negative K2 A1. So here, actually, let me write a few more steps just to be a little bit, sorry, I can start here and plug this in. So I get K1 plus K2 minus K1 minus K2, minus 2K2 A1 equals K2 A2. So here, K1s cancel out, and I get A1 equals negative A2. So I have the same mode that I had before. So I either have the two masses moving together or moving opposite each other, moving completely out of phase. So then I get, what we started with is that we solved it in the case that the two masses were equal and we didn't have, we saw that we got these two solutions. Then I solved it in the general case, and we still get the same two solutions. The frequencies vary. Now, if you look at K1 being much less than K2, then almost everything is close to your natural frequency because this correction is very small. So we can then write, let me switch colors because this is still very general. But we could write omega naught is the average of our two frequencies. And then our first frequency is omega naught minus some small shift. Our second frequency is omega naught plus some small shift. And in general, we can write our solution. I'm going to use Z, and you can just take the real part of it in your head. This is our first solution. And this is our second solution. So what we actually see is that over a short period, all of the oscillations are with omega naught. And over a large period, you will see that it looks like beats. So you have over short periods, it looks like oscillations with a constant frequency, but the amplitudes are going to be changing. So the oscillations between the two parts oscillates itself slightly. You could write then x is some constant cosine epsilon t cosine omega naught t in the case of zero phase shift, and I will be lazy. We're looking at the qualitative features, and the phase shifts don't change what happens. So it oscillates between the relative magnitude is oscillating between the two parts. Okay, so now we're going to take the same approach, but we're going to solve a slightly different problem. So we're going to solve a double pendulum. And what I mean by that is that we have a pendulum of mass m1 on a massless string oscillating at angle phi 1. This string has length L1. So far, so good. This is pretty normal. But then we have it attached to a second pendulum with mass M2 and L2, and then we have an angle phi 2. So then, now the zeros don't matter for the potential as much. We're going to write the potential. It is M1 for mass 1 is M1G L1 1 minus cosine phi 1. So that is the height above its this is the height above its equilibrium position. L1 times 1 minus cosine phi 1. And the potential for the second mass is M2 G L. And that actually we're going to have two terms. One is it's lifted by the same height above its equilibrium position that mass 1 is. So even if phi 2 is 0, this thing is still, this mass is still slightly above its height, its equilibrium height, plus L2, 1 minus cosine phi 2. So far, so good. T1 is easy. This is 1/2 M1 L1 squared phi 1 dot squared. That's because this is then fixed. It is always going to be a length L1 from the pivot point, and then there is no velocity in the r hat direction, and the velocity in the phi hat direction is L1 times theta dot. Now, for the second kinetic energy, I'm going to write V1 as L1 phi 1 dot sine phi 1, L2 phi 2 dot sine phi 2, and then V2 is the sum of the velocity. And now here I have written a coordinate, I've assumed a coordinate system here, X and Y. V2 is considerably longer. I have an L1 term from the velocity of the first mass and an L2 term this should be a cosine. So for V1, when I square it, I get a sine squared phi 1 plus cosine squared phi 1, which goes to 1. And then here I have this, but with cosines instead. The book just sort of says, this is the kinetic energy. But I'm going to work it out for you a little bit more. So then, when I square this, I take the dot product of the vector with itself. So we are then left with L1 squared phi 1 dot squared sine squared phi 1 plus L2 squared phi 2 dot squared sine squared phi 2 plus the cross terms 2L1 L2 phi 1 dot phi 2 dot sine phi 1 sine phi 2. Take a breath. Plus, that's just the x term squared, L1 squared phi 1 dot squared cosine squared phi 1 plus L2 squared phi 2 dot squared sine squared phi 2. This should have a 2. Sine phi 2 squared plus 2L1 L2 phi 1 dot phi 2 dot cosine phi 1 sine cosine phi 2. And these terms add up to L1 squared phi 1 dot squared. That's this guy. This should be a cosine. I made a mistake. Sometimes you can tell your mistakes by looking at symmetry. All these should be cosines. Okay, so then this term and this term add up to simply be L2 squared phi 2 dot squared and no cosine. So far so good. This term is then 2L1 L2 phi 1 dot phi 2 dot sine phi 1 sine phi 2 plus cosine phi 1 cosine phi 2. and I forgot to underline this in a certain color. These guys are this. Now, this thing happens to be cosine phi 1 minus phi 2. So, all of the v2 squared terms add up to be L1 squared phi 1 dot squared plus L2 squared phi 2 dot squared plus 2L1 L2 phi 1 dot phi 2 dot cosine phi 1 minus phi 2. Big, ugly mess. Okay. That leaves us with, let me see if I have enough room for, I don't know that I can squeeze the Lagrangian in there. So we're going to wrap it over a couple lines. The Lagrangian is 1/2. I'm going to do group the M1 and M2 terms there. M1 plus M2, L1 squared phi, this should be a 1 dot squared plus 1/2 M2 L2 squared phi 2 dot squared plus, because I multiply this by 1/2 M2, so I am left, the 2's cancel out, but I get an M2 L1 L2 phi 1 dot phi 2 dot cosine phi 1 minus phi 2. I want to leave myself a little bit of room. And then all of the potential terms, negative M1G L1 1 minus cosine phi 1 minus, let me actually write the next term on the next line, M2G L1 1 minus cosine phi 1 plus L2 1 minus cosine phi 2. All right, that gives me the Lagrangian. This thing is an unworkable mess. We will not be able to solve the, even if we did the, we would not be able to solve this in general because of the cosines and sines and the derivatives. You would have a second order differential system of second order coupled differential equations, and you could solve it numerically. And at least the students in my class learned how to do that last semester. But in general, we can't solve it analytically. We are going to do instead what often physics boils down to, which is take a Taylor series and look at the small angle approximation. So we're going to work in the case that both of those angles are in fact small. So then we're going to approximate the Lagrangian and get it to something that we can actually work with. So we are going to use a few different approximations. So the big one, we've got all these cosines in our Lagrangian. We're going to use the Taylor series. We've got 1 minus cosine phi. That shows up a lot. Cosine of a small angle is approximately equal to 1 minus 1/2 that angle squared plus higher order terms. So if we look at these and we drop the first non-zero term, we're going to be left with 1/2 phi 1 squared. So we can take our Lagrangian and work through and come up with an approximation that leaves us with something workable. What we're going to see is that this is then something like what we had with coupled masses and springs. This acts like a coupled oscillator, unsurprisingly, because when we had a simple pendulum, it acted like an oscillator. It acted like a mass on a spring. So now we have something similar. We don't need to approximate these terms because they are linear and not funky terms. When we get to this term, if these are each small angles, then the difference between them is a small angle, and we're actually going to approximate this as not, we could, if we wanted a higher approximation, approximate it as phi1 squared minus phi2 squared, but we're just going to approximate it as 1 because each of these is fairly small. That is going to leave us with M2 L1, now this should be an L2, L2 phi1 dot phi2 dot, you can't see the dots there. So I'm going to have to move this just, let me make the dots. Phi1, phi2. Minus M1G L1. We're going to replace that cosine by a 1/2, 1 minus cosine phi1 by a 1/2 phi1 squared minus M2 G, we're L1, and then this we're replacing this term by 1/2 phi1 squared and here we have an M2 G L2 1 minus cosine phi2, which we will replace by 1/2 phi2 squared. And then our Lagrangian looks rather simple, doesn't it? It looks much simpler than it used to be. So we will, let me just change equations to make it, change colors to make it stand out. The phi1 equation is partial L partial phi1 equals, we've only got, let's see. Yeah, we've got this term and that term. So I am left with negative M1 plus M2 because these two terms are identical except for the M's. G L1 phi1 partial L partial phi 1 dot is, I've got a phi1 dot here and a phi1 dot there. So I get an M1 plus M2. The 2 comes down. I have an L1 squared and a phi1 dot. And then I take the derivative of this term. So I get an M2 L1 L2 phi2 dot. And then I'm going to take the time derivative, and I add a dot to my phis. Phi2 equations are partial L, partial phi2, here, the only time I have a phi2 is here, and this should have been a negative sign. I am just making typos left and right today. These equations in this lecture are all ugly. They're not actually complicated, but it's a lot of ugly equations. All right, now I have a negative m2g L2 phi2. Partial L, partial phi2 dot. Here, I've got this term. I've got a phi2 dot here and a phi2 dot there. So now I get m2 L2 squared phi2 dot plus m2 L1 L2 phi1 dot. Take the time derivative, and I add another dot. So this leaves me with, I can write then these equations as m1 plus m2 L1 squared L1 L2 m2 m2 L1 L2 m2 L1 squared times phi1 double dot phi2 double dot equals negative. So I will go back through this in just a second. m1 plus m2 g L1 0 0 m2 g2 L2 phi1 phi2. Okay, so how I got that is that I have this side of this equation, which the coefficient of phi1 double dot is m1 plus m2, and the coefficient of phi2, m1 plus m2 L1 squared, the coefficient of phi2 double dot is m2 L1 plus L2. And then this is equal to that, so I have a negative m1 plus m2 GL times phi1. My second equation, I have the coefficient of phi1 double dot is m2 L1 L2 phi, the coefficient of phi1 is m2 L1 L2. The coefficient of phi2 is m2 L, this should be an L2 squared. And that's why we check our work. And then that is equal to a negative m2 G2 L2 phi1. You may, if you're not as familiar with matrix equations, need to take a minute to digest that. Okay, so we are then going to assume a solution that the angles are the real part of A1, A2, e to the I omega t, and try to find that omega. This is our mass matrix. This is our spring constant matrix. And then K minus omega squared m is m1 plus m2 quantity times G1 L1 minus omega squared L1 squared. That is from the m times omega, this should be looking at the wrong matrix. Yes, this times omega squared and then this term here, and then I have K m1, K is in this, I'm going to write out my matrix. So in this term, my K is 0, and then minus omega squared m gives me a negative omega squared m1 L1 L2. Here, K gives me a 0 minus omega squared m. And then in this term, I have K m2 g2 L2 minus omega squared times the component in the matrix. So this is big and ugly. And at this point, I'm going to deviate from solving it generally because the book only solved it in certain cases, and I don't know how to go further. So not without, it would get really ugly. So in principle, when we take the determinant of this, we get a quadratic equation in omega squared. You can plug it into your quadratic equation. You can solve it, but it is ugly. So we are going to look at the case that was done in the book, which is that the two lengths are equal and the two masses are equal. When we do this and plug, we are then going to use omega naught equals G over L, and K minus omega squared M, this thing, we're going to pull out an M L squared, so wherever we have a G, we're going to end up with G over L, and otherwise the terms all have M's and L's. So here I have two M's, so I have a 2, I have a G over L, so I get an omega naught squared minus omega squared, and here I have a minus omega squared, which I also have here. These matrices will always end up symmetric. And here I have an omega naught squared minus omega squared. So that becomes this matrix. I now want to take the determinant, set it equal to 0, and solve for omega squared. So I get 2 omega naught squared minus omega squared, quantity squared, minus omega to the 4th equals 0. And there is an ml squared out in front, but we can divide it through by that so that we do not have, well, let me just leave it there for the moment. So then we're really looking at solving this for that equals 0. So I'm going to expand this term. I get 2 omega naught to the 4th minus, or let's see, plus a 2 omega to the 4th minus 4 omega naught squared omega squared. That's just from the cross term. And then minus omega to the 4th. So this cancels out that. And I am left with omega to the 4th minus 4 omega naught squared omega squared plus 2 omega naught to the 4th. And I can use my quadratic equation. I'm going to erase a little bit in order to get some room. My omega squared is negative 4, so negative b, this is b, plus or minus b squared minus 4ac. So I have a 1 times 4 times this. So 8 omega naught squared, square root of that, divided by 2. That doesn't contrast. I want to use this. So I'm left with a 2 here. And then here I'm left with an 8 and a 4. When I divide through by the, no, I am left with a 4 and a 2. So here I have 2 plus or minus the square root of 2 omega naught squared. All right, so those are my two solutions. And then we can look at omega 1 squared equals 2 minus the square root of 2 omega naught squared. Plug that into k minus omega 1 squared m. And I had to erase a lot to make the board clear. We get ml squared omega naught squared square root of 2 minus 1 2 negative square root of 2 negative square root of 2 1, and this times a1 a2 has to equal 0, so we get 2a1 minus the square root of 2 a2 equals 0, which if we pick a, so a2 equals then the square root of 2 a1, so we will use 1 square root of 2 as our first mode. Omega squared omega 2 squared is 2 plus the square root of 2 omega naught squared. And then we will get something very similar. We get k minus omega 2 squared m is negative, I have the negative sign there, negative ml squared omega naught squared square root of 2 plus 1, 2 square root of 2 square root of 2, 1. This has to equal 0 for when this times a has to equal 0, so we get 2 a1 plus the square root of 2 a2 equals 0, and that one of the solutions to that is this vector here. So we have two modes, like what we had when we had the masses on the carts on springs. We have one mode where they are moving together. The two pendulums are going like this. And then we have one mode where they're moving opposite each other. Sort of looks like a dance. So they either oscillate in phase or they oscillate out of phase. And either way, the second pendulum is oscillating with a mass which is the square root of 2, with an amplitude which is the square root of 2 larger than the amplitude of the first pendulum. So I think what that really shows is that you can take this methodology, and if you can write your Lagrangian in terms so that you have phi 1 dot squared, phi 1 terms and phi 2 terms, you can have, so here this should be phi 1 term, phi dot terms of the second order, and here you can have phi terms of the second order. You can't have cross terms, which actually, by the way, here, if we had not approximated this at 1, we would have had cross terms, and then we wouldn't have been able to do this. Arguably, those terms can be significant, and that is a reason why this might not quite fully describe the full motion. What we're going to get into later is showing how you can do this in general, even if you don't have angles. We can then talk about what happens in the general case. So if we have an object that is, there's some equilibrium point, and we have n degrees of freedom about that equilibrium point. That could either be in one dimension, you have n different masses connected to springs, or it could be that in 3 dimensions something can move in 3 directions. 3-dimensional masses and springs, you have 3 degrees of freedom in each direction, but you might have more than one mass. So you have n degrees of freedom total. Then we can write the position as just the qi Q1, Q2, Q3 to Qn. And we're going to explicitly choose to have these be 0 at the equilibrium position. Remember, a good physicist is a lazy physicist. So why not choose the easy answer? You can always shift your coordinate system so that the 0 is where the q's are 0, you have the equilibrium position. So this is now an n-dimensional vector which is in the space of generalized coordinates. A little bit abstract. It does not have to be positions. It can be angles. It could be anything that just, any variable that describes the system. And we're going to assume that the system is conservative so that we can write the potential as a function of the Q's. So we will say that this is, the potential is a function of the generalized coordinates Q. Now, the kinetic energy is always 1/2 times the sum of the masses. So if we have, so if we are talking about the positions, X, Y, and Z, we would write it as this, where for one mass, there's going to be an X dot squared, a Y dot squared, and a Z dot squared. So these are not all, they don't all have to be for the same mass. They can be for different masses. If you had 3 masses, alpha would run, 3 masses in, which can move in all 3 dimensions, alpha would run from 1 to 9. And here I should have M alpha. And we want to rewrite this in terms of the QI dot. We will assume that there is no explicit time dependence because we are assuming that we have a conservative potential. And we are going to assume that the position vectors, the position vectors are a function in general of the Q vector. So you can write the position vector in terms of the generalized coordinates. So to think about a concrete example, if our generalized coordinates are theta, phi, and r for spherical polar coordinates, then you can write x, y, and z in terms of theta, phi, and r. And likewise here, when you did the kinetic energy, you would have an x term, a y term, and a z term, and you could, to get that kinetic energy, you can take the time derivative of the position vector written in terms of r, theta, and phi, and square it, and you will get it's ugly, but you could do that with spherical polar coordinates. So in principle, it's true, it's ugly, but it gives you a prescription which will always work. All right, so then that means that we could write, because if we can write the position vector in terms of the generalized coordinates, that means that we can write the kinetic energy in terms of the generalized coordinates. So we're going to write this as the sum over jk, a, j, k, q, j, dot, q, k, dot. This will start to look familiar because if you've had a little bit of linear algebra, you know that you can write a matrix with subscripts. So this actually is describing a matrix. All right, so if we assume small oscillations about the equilibrium position, and we define Q equals 0 to be the equilibrium position, or we use that to define the equilibrium position, then, as with many things in physics, we can Taylor expand. So we're going to take a Taylor expansion. And you guys haven't really seen Taylor expansions in more than one dimension, but this will look familiar from Taylored expansions in one dimension. We can write the potential as the potential evaluated at 0, where this is now our equilibrium position, plus the sum over all of the different Qn, partial U, partial Q, this is a J, partial QJ times QJ. So this is just the term in the Taylor expansion. This is taking the first derivative and multiplying it by the variable minus the variable at equilibrium, except now the variable at equilibrium is 0 because we have chosen the Q equals 0 to be equilibrium. A good physicist is a lazy physicist. Plus 1 over the 2 factorial, which is just 1/2. And now we take the second derivative, but now because we have more than one variable, we have to have variables versus as a function of two different. We have derivatives in principle, which can be a function of two different variables. So we're going to have jk in the sum here, partial u squared, partial qj, partial qk, qj, qk plus ... Now, we have chosen, not by accident, to set our q's to be 0 at the equilibrium point. This is just a constant, so we can redefine our potential so that this is 0, because that makes life a lot easier. You can always shift your potential so it's 0. And then this term, you are at equilibrium, and when you are at equilibrium, the first derivative is 0. So, because we are at equilibrium, this guy is 0, and we are left with this thing. That means that we can write our potential, u, as a function of q vector, as 1/2 k j k, this is the sum over j and k, q j q k, where k, let me write it, I'm moving towards a matrix, but I'm not yet ready to do it, where k j k is partial u, partial q j, partial q k. And if you guys are comfortable with matrix notation, which if you're a physics major, if you're not already, you will be, whether you want to be or not, you will notice that this is the same thing as, this is saying that u is equal to 1/2 q vector transpose k matrix q vector. So this is the n-dimensional spring potential, and basically what we have done is say that that we're expanding about an equilibrium point, and when we expand about an equilibrium point, we just get an n-dimensional mass on a spring. And then we can come back to t and this aij term, or say ajk term, and the ajk term is, so everything in t is already small. Now it's already, we're talking about small displacements from equilibrium. So we have a qi dot squared. So we only have to worry about first order terms. We don't have to worry about terms that have extra orders of the q in them, because those will be even smaller. So the a, j, k evaluated at q equals 0 are equal to, now you can see where we're going, that's equal to the entries of the matrix M. So then we can write that our potential energy is 1/2 times the sum over J and K, M, J, K, Q dot J, Q dot K. And this is, in matrix notation, 1/2 Q transpose M, or Q dot transpose M Q. So this means that the kinetic energy is a quadratic function, the kinetic energy is a quadratic function of the, missed a dot there, of the qi dot, and the potential energy is a quadratic function of the q's. So we can solve this with linear equations, because that is telling us that where we have an equilibrium position, we actually end up with a Lagrangian of the form 1/2 q vector dot m q, I need a transpose, q dot vector minus 1/2 q vector transpose k q. So this is our previous system of equations, just like what we had for the system of masses connected with springs. So this is a set of solvable linear equations. So I think it is worth pausing for a minute and talking about the significance of this. What we just showed is that if you have an arbitrary system that has an equilibrium point, you can describe slight perturbations from that equilibrium point as like a mass on a spring. So this esoteric problem that you probably first saw when you were in introductory physics, and if you were like me, you're going, okay, I can solve this problem, but why do I care? Because how often do I just sit there and hang a mass on a spring and just twiddle around and play with it? I don't do that. But I can always describe something with a Taylor series. Not to arbitrary accuracy, but a pretty good accuracy. In many cases, when you have a system which is roughly at equilibrium, and I can describe oscillations about that equilibrium point as a mass on a spring, arbitrarily in 3 dimensions with n particles, it doesn't matter. Any system in equilibrium is approximately a mass on a spring. It always has a first derivative, which is 0. It always has there will be a constant second derivative. It's always a mass on a spring. I didn't appreciate that when I was in undergrad. I appreciated that when I got to graduate school, and I don't know why anybody didn't why this was never emphasized to me, at least when I was an undergrad, or maybe it was and it didn't sink in. So I want you to sit with that, because sometimes when you're in the middle of this, you spend so much time focusing on whether you understand a given line and all of the derivations that you sort of can miss the point. And the point is that everything is just a mass on a spring. All right. So then we will go through example 11.1, and here you have an arbitrary bead on a wire, and we are going to, so we have x positions, an x position and a y position, and it's a squiggly wire, and there's some equilibrium point, and we can write y as a function of x for the wire as, we can write y as a function of x for the shape of the wire. Then if we want to describe the potential is mgy times the height, and the height is now f of x. So this is mg times the Taylor series of f, which we've chosen to have x be 0. So this is f of 0 plus f prime of x times x plus 1/2 f double prime of x times x squared plus higher order terms. Now, we have set our coordinate system so that this is 0 at the low point, and this is an inflection, or this is a minimum, so the first derivative is 0, as it should be a 0. And this should be a 0. The first derivative is 0, so we are left with u equals 1/2 mg f double prime evaluated at 0 x squared. So this has the same form as the potential for a one-dimensional mass on a spring. The kinetic energy is 1/2 m x dot squared plus y dot squared. I want to write things in terms of x dot squared, so I'm going to try to write y dot squared in terms of x dot squared. Y dot is dy dt, and this is the same thing as dy dx dx dt. So this is just what we have called f prime of x. So up here, when we took the derivatives, we were writing f as a function of x, so this derivative is with respect to x, and times x dot. So here I can write and then then I can write this further as approximately f. No, I don't want to. Yeah, I can still write this as approximately f prime of 0 x dot, but this is just 0. So I can come here. This is 1/2 m x dot plus f. I'm going to pull the x dot out. So I have 1 plus f prime of x dot squared, but I can take the Taylor series of this, and that first term, well, this is not, I don't take a Taylor series, this is just the derivative, but I can expand it about x equals 0, so this just simplifies to roughly 1/2 m x dot squared, because this term is approximately equal to 0. So then I get a Lagrangian, which is 1/2 m x dot squared minus 1/2 m g times the second derivative with respect to x, evaluated at 0, of f x squared. And this is simply the form of a mass on a spring. So if I want to describe the motion of a bead on an arbitrarily shaped wire around the minimum, it is always approximately a mass on a spring. It's going to have some sort of oscillatory motion about the equilibrium point, and my spring constant will be slightly different depending on what that second derivative is, but it always has the form of a mass on a spring. So then what we can do is look at this equation of motion in more detail, and I asserted that I could write it as a matrix, but we're going to set this up so it's a little more obvious that you can write it as a system of equations. So the equations of motion with the Euler-Lagrange equation, let's see, mind telling me where I have to stop writing. We can write this as d dt partial L partial qi dot equals partial L partial qi. So then we have however many generalized coordinates there are, we have that many equations. By the way that I remember this is units. So ddt has units of 1 over time. This has units of q over time. So the 1 over time and 1 over q over time leaves units of 1 over q. And then I have a 1 over q here times the units of the Lagrangian on both sides, which are units of energy. But regardless, the ddt units here cancel out the dt units here. And that's how I remember it. Because a good physicist is a lazy physicist. And one of the characteristics that frequently distinguishes physics majors from other majors is that physics majors would rather derive 5 pages of algebra than memorize an equation. So then we will look at the case in particular of 2 dimensions. So we have qi equals, the I runs from 1 to 2. And then in that case, our potential, which was 1/2 sum over j equals 1 to 2, sum over k equals 1 to 2, k, j, k, q, j, q, k. This is 1/2 k, 1, 1, q, 1, 1 plus k, 1, 2, q, 1, 2 plus k, 2, 1. I'm doing subscripts on the q's and I don't want to do that. q1, q2 plus k1, 2. This should be a 1. What is with me today? All right. q1, k11, q1, q1, k22, q1, q2 plus k21, q2, q1 plus k22, q2, q2. This is all equal to 1/2 k 1, 1 q1 squared plus 2 k1, 2 q1, q2, because this term is equal to that term. It just changes the order you do derivatives. Mathematicians would worry about that. Physicists always work with nice, neat, smooth functions where we can get away with that. And then I have k22 q2 squared. And then when I look in particular at the 2-dimensional case, partial u, ooh, that's not visible. You will choose. The orange marker is visible. Partial u partial qi equals the sum over, sorry, qj equals the sum over qj ki j qj. I screwed up my, no, this one should be an I. So I am taking the derivative with respect to qi, and then when I have a qi, that fixes the k to be equal to I, and the other is equal to j. What that means in terms of one dimension is that partial u partial q1, looking back here, is equal to k11 q1 plus k12 q2. All right, then for partial, so we had a t of 1/2 jk m jk q j dot q k dot. So partial t partial qi dot is equal, again, I'm going to fix the k when I take that derivative. So this is equal to the sum over j m j I q j dot q I dot. And when I take the time derivative, I add, well, that's, I did not, so here I actually should have kept the qj dot and not put the qi dot. And when I take the time derivative, I just add a dot there. So in one, if we again look at the case of two particles, I have 1/2 m11 q1 dot q1 dot plus m12 q1 dot q2 dot. It is symmetric, so the next term looks the same, plus m22 q2 dot q2 dot. And then when I take this derivative, I do partial t partial q1 dot. This is m11 q1 dot plus m12 q2 dot, and the time derivative adds a dot. And then we can write our Euler-Lagrange equations as this. In practice, this turns into partial t partial qi dot d dt equals negative partial u partial qi. Because we don't have any time dependence, there's no qi dot dependence on u, and there's no q dependence on t. So this is another way to write our Euler-Lagrange equations, and we can write the Euler-Lagrange equations for this system as this thing equals the negative of that thing. This is so the ith equation has sums over j. And that is, I'm not following a very good linear path. We'll write it down here. That is just another way of writing the mass matrix M times Q vector double dot equals negative K matrix Q, or so this has solutions, as we saw in the previous sections, K matrix minus omega squared M, where that determinant is equal to 0. That gives us the omega, and that omega is paired, which is the eigenvalue, is paired with K, the solutions of K minus omega squared M times A equals 0. And this is an n-dimensional equation, so this has n solutions. So there are n different frequencies. If you have n degrees of freedom, you have n different eigenvalues and eigenvectors. Now the eigenvalues can repeat themselves, and in that case the eigenvectors are not linearly independent, but it will in principle have n different solutions. So we can then take this and apply this to a specific example, and that's all that section 11.6 is a big, long, specific example. It's particularly gnarly and ugly, but what it's demonstrating is that I can in fact come up with an ugly problem that would be nearly impossible, or at least insanely difficult, to approach using, at least analytically, to approach using the tools that we have with Newton's laws and not making any approximations. We can actually solve we can solve when we make approximations for these gnarly, ugly problems using Lagrangians and some reasonable approximations. So here we have 3 coupled pendulums. They have 3 angles. Phi 1, Phi 2, Phi 3. We are going to choose, so that the problem is not too crazy, that they all have masses M and lengths L. I maybe drew that too big. I might regret it later. Now, they are constrained to move on the string, so we can write our kinetic energy is 1/2 m, and then the velocity of this bob is L phi 1 dot, so the velocity squared is L squared phi 1 dot squared, and then it's the exact same form for each of the other 2. And that is with no approximations. Now, I'm going to set my 0 of potential to be when the bobs are at the very bottom of their path. And when I do that, my potential is going to be mgl 1 minus cosine phi 1 plus 1 minus cosine phi 2. That's because this height here is L times 1 minus cosine phi 3. So that height is 1 minus cosine of the angle. So I've got 3 of these terms. Now, we can always write cosine of a small angle, because it's a Taylor expansion, as 1 minus 1/2 times the angle squared. So we're going to do that. And then we get a potential, which is approximately mg at 1/2 mgl. This term becomes phi 1 squared. These terms become phi 2 squared. These terms become phi 3 squared. So I have phi 1 squared plus phi 2 squared plus phi 3 squared. Now, I could have defined my 0 of the potential to be basically anything, but I chose to, and this is the gravitational potential. I forgot to say that. That is important. The gravitational potential is easy. So this is my gravitational potential to good approximation. I'm going to have to consider, I forgot the next part, which is that they are connected by springs with a spring constant K. So the gravitational potential is fairly straightforward. If these are connected by, because it wouldn't be a coupled system if they weren't connected by springs. It would be kind of boring. So if they are, so when they're connected by springs, our spring potential is 1/2 K, and then the displacement from equilibrium squared. And now, as long as we are in the small angle approximation, the displacement is L times the angle, the angular distance from equilibrium. So for the first spring, it is phi 2 minus phi 1. That is that if phi 2 and phi 1 are the same, the spring is not stretched, and then I have to square that. And then plus L squared phi 3 minus phi 2 squared. Now, note here that you're making the approximation that most of the motion is basically linear. You're not worrying, like, if this mass goes up really high and this one stays low, the spring is actually tilted and you have some 2D motion of the spring. So figuring out how stretched the spring is a little bit more complicated. The book leaves that as an exercise for the students. It's one of the homework problems. I'm not going to assign it. It's ugly. To figure out exactly what that is without approximating. So we're just taking the approximation before we write this all down. This is 1/2 K. I'll pull an L squared out. We have a phi 1 squared, a phi 2 squared, and minus 2 phi 1 phi 2 plus phi 3 squared plus phi 2 squared minus 2 phi 2 phi 3. And overall, this is 1/2 KL squared phi 1 squared plus 2 phi 2 squared plus phi 3 squared minus 2 phi 1 phi 2 minus 2 phi 2 phi 3. The book uses natural units, so what the book does is sets L and K equal to 1, L and K and M equal to 1, and then you figure stuff out at the end. I don't think that we need to add that conceptually at this point, so I'm going to do it out without natural units. What I'm going to do here, so I'm going to be lazy. I'm going to write down the whole Lagrangian, and then I'm going to do a little bit of cleanup. So our Lagrangian is then the kinetic energy minus this mess. Okay, so now we can write out our Euler-Lagrange equations. This is going to be a doozy. We'll make it through. So we will start with partial L partial phi 1, which gives us a negative MGL phi 1 minus KL squared phi 1 and then here I get I can actually write this phi 1 minus phi 2 because I have this term in there too. And this is all equal to partial L partial, the time derivative of partial L partial phi 1 dot. So that's partial L partial phi 1 dot. And that's my time derivative of that. So this is d dt partial L partial phi 1 dot. Then I have my equation for phi 2. That is going to give me negative mgl phi 2 minus kl squared. And then here I have two phi 2 minus phi 1 minus phi 3. Let's just take a little second on that one. So here I have a factor of 1/2, and when I take the derivative here, I get another factor of 2, and I have another factor of 2. So I get a 2 overall. And then the factor of 1/2 cancels out the 2's on those terms. And then I take the derivative with respect to phi 2, and I get a phi 1 and a phi 3. And then the time derivative with respect to, the derivative with respect to phi 1 dot has the same form as phi 2 dot. And then I take the time derivative. And then our phi 3 term is going to look more like the phi 1 term. So, negative mgl phi 3 minus KL squared. Here I get a phi 3, because when I take the derivative, I get a 2. It cancels out that 2. And then I get a minus phi 2. So it has the exact same form as the phi 1 term. And this is equal to ML squared phi 3 double dot, which is d dt partial L partial phi 3 dot. All right. Then I can divide through, now these are my equations. All that strictly speaking matters is that I can write this as a system of matrix equations. So I want my matrices to be as nice and neat as possible. I am going to divide through by ML squared. And you will see that then this starts to look kind of familiar. At least you will meet some old friends, L over G and K over M. Okay. And I'm going to rewrite the, well, actually, let me get the matrix equations and then I'm going to move them over here. I'm going to define, this is slightly different from the way the book, from the notation the book uses. I'm going to define omega G squared as G over L and omega K squared as K over M. And then I can write this set of equations, well, I can write this set of equations as, I only have one phi 1 double dot, phi 2 double dot, and phi 3 double dot. So that one's easy. So my mass matrix is 1 0 0 0 1 0 0 0 1, or the identity matrix. And my K matrix is then given by here, the coefficients of phi 1 are omega G squared plus omega K squared in this equation. The coefficients of phi 2, are omega K squared. There are no phi 3 terms. The coefficients here of phi 1 are negative omega K squared. The coefficients of phi 2, and I'm trying to write it as a negative, the negative of this sign, of this equation. So the coefficients of phi 2 are omega G squared, and then plus 2 omega k squared. And there is the coefficient of omega 3 is negative omega k squared. Down here, the coefficient of phi 1 is 0. The coefficient of phi 2 is negative omega k squared. And the coefficient of phi 3 is omega g squared plus omega k squared. And I'm going to move my m down here. Okay, now what I'm going to do is solve this, but I want to stress that this problem, especially because you guys are upper division undergraduates, for many of you it is your first upper division physics class, like it looks really hairy and ugly, and it is. Don't miss the forest for the trees. The thing is, I'm showing you how you can solve it in general. In practice, should you be doing this, you're going to solve it with computers and the aid of computers. Now you can look at this, the set of equations that we had before was gnarly and ugly, so the odds that you would make a mistake are pretty high. You should end up with symmetries. So your matrix, both matrices, should be symmetric. So if you flip them about the diagonal, they should be the same. Negative omega k and everywhere. So this is diagonal. If you swap it around the diagonal, it's symmetric. So then another thing that you can see if you look at the problem is symmetric if you switch the first and the last pendulums. So here, these have the exact same forms because there's no difference. I could just have renamed them and the problem would be exactly the same. So you can use that to check your work. Now, what we're going to do is solve the equation. We're first going to look at the determinant of k minus omega squared m. A good physicist is a lazy physicist. So I'm going to squeeze this in, minus omega squared m, and I'm just going to add an omega squared. Now this gets a little confusing. M is diagonal, so I just add a minus omega squared here, everywhere. I don't want to have to rewrite that thing to take the determinant. If we look at k, it's just the blue parts. If k minus omega squared m, you have to add the things that look orange to you. Now, this determinant, k minus omega squared m, it's this term, omega g squared plus omega k squared minus omega squared times the determinant of this submatrix, which, I actually don't, I want to use a big bracket. I am going to wrap this around because I don't think I have room. Omega g squared plus omega k squared minus omega squared times the determinant of this submatrix, which is this term, omega g, this is missing a 2. That was a typo. omega g squared plus 2 omega k squared minus omega squared times omega g squared plus omega k squared minus omega squared minus a minus omega k quantity squared. So I end up with a minus omega k to the 4th. And then minus omega, it's minus because I move one column over. So minus a minus omega k quantity squared times the determinant of this submatrix, which is negative omega k squared times omega g squared plus omega k squared minus omega squared. Okay, so dumb things. There's ample room for dumb algebra mistakes in here. So be cautious. What we can do here, so how do you catch dumb algebra mistakes? One thing is the buddy method. Use two people. Another way to avoid, so if you and your buddy both get the same answer, it's probably right. Another way is to use a symbolic math program to check your work. I do recommend that you try to do it by hand first, because the more you do it by hand, the better you're going to get, but you're also going to get better at seeing mistakes. And there actually are a number of cases when symbolic math programs don't work super well. And then double check your work. But notice here how I was being a little bit more explicit. You might be in the habit of doing these sign changes by yourself and in your head. Write it out more explicitly because you're less likely to make dumb mistakes. And let me be perfectly honest that the first time that I wrote my notes out and I tried to solve this by hand, I made a lot of mistakes and I had to redo it. Actually, I don't know how many mistakes I made. One mistake still gives you a wrong answer, and you might not catch it till you're 10 steps down. Okay, now this factor, we're solving this equals 0. So this factor is out in front everywhere. So one of my solutions has omega g squared plus omega k squared minus omega squared equals 0. The other two solutions have omega g squared plus 2 omega k squared minus omega squared omega times omega g squared plus omega k squared minus omega squared minus omega k to the 4th. And then there's two of those because this term ends up being minus omega k to the 4th. So I need a 2 omega k to the 4th out here. That's all equals 0 for the other two solutions. This one, I can say one of the solutions has omega squared equals omega g squared plus omega k squared. And to match the numbering in the book, I'm going to call this omega 2. Now, we're going to multiply this thing out and solve it with the quadratic equation. So, bear with me here. Feel free to skip over this part. This is just me doing ugly algebra. I get omega g to the 4th from this times this plus omega g squared omega k squared minus omega g squared minus omega squared plus 2 omega k squared omega g squared plus 2 omega k to the 4th then this minus 2 omega k squared omega squared. That barely fits, but we'll let it sit. Then this term multiplied through minus omega squared omega g squared minus omega squared omega k squared minus omega to the 4th. And then this guy comes along for the ride. Minus omega k, it should have been to the 4th. That all equals 0. Now I'm going to combine terms. I'm going to underline them so that they stand out. Okay, so first of all, these guys just cancel out. So I don't have to worry about them anymore. That's good. Then this term and this term are can be combined because they have the same form. This one is a times, not minus. This term and this term can be combined. These two terms can be combined. And I'm a little short on colors, so we do squiggly. They don't stand out as much, but they're squiggly. Okay, so then I'm going to purposefully order it because I'm going to apply the quadratic equation. I have a, let's see, this should have been a plus omega to the 4 because that came from that. So my omega to the 4th term is there. And this term and that term have omega squareds in them. So I have a minus omega squared, and then this is 2 omega g squared, and these guys add up to 3 omega k squared. And then everything else. So I've got these, and I need to add up. First of all, I have omega g to the 4th, and then these terms, plus 3 omega k squared omega g squared, all equals 0. And then I have negative b, so 3 omega k squared plus 2 omega g squared, plus or minus the square root of b squared, and I'm going to, my negative sign drops out when I square it, so I have a 4 omega g squared plus 9, or g to the 4th, plus 9 omega k to the 4th, plus 2 times 3 is 6, times another 2 is 12 omega g squared omega k squared. Let me start writing my square root, minus 4ac, so minus 4 omega g squared minus 12 omega k squared omega g squared. all over 2a. And then we have some simplifications in here. A lot of them. These guys cancel out. These guys cancel out. And we are left with, and this was omega squared equals, so omega squared equals 3 omega k squared plus 2 omega g squared plus or minus 3 omega k squared all over 2. This gives us our other two solutions. Which are here, 3 minus 3 gives us omega squared equals omega g squared. And we will call that, I think that's omega 1. And then omega 3 squared is 3 plus 3. So 6 divided by 2 is 3 omega k squared plus omega g squared. So now we have our eigenvalues, and what we need is our eigenvectors. I'm going to clean this up a little bit. Okay, so then we can look at each of these individual eigenvalues and figure out the eigenvectors. So we first, to do that, we are going to look at the equation k minus omega squared m times a vector a full of constants and figure out what a works for each of the omegas. So for omega 1 squared, which is omega g squared, I'm going to put a box around it. This is where we're going to work on that. Our k minus omega squared m is, now we're subtracting, so here we have an omega k squared, and then negative omega k squared, negative omega k squared. Here we have 2 omega k squared, 0, negative omega k squared, negative omega k squared, 0, omega k squared, and then times a1, a2, a3. This, so we can divide out by a factor of omega k squared, and this all has to equal 0. And so we get 1, negative 1, 0, negative 1, 2, negative 1, negative 1, 0, 1, a1, a2, a3. The omega k squared can be canceled out because we can divide through by omega k squared. And then we get the first equation is a1 equals a2. The last equation is a2 equals a3. So we get a is 1, 1, 1. Now, I can choose this up to a scale, so this is what I choose. What this means is that all of the pendulums are moving together. So there's no dependence of the frequency on omega k, because the springs are not compressed and the springs are not are not stretched. Now, I don't know if I can fit all of the eigenvalues in eigenvectors into one board, but we'll see how far I get. I have omega 2 squared equals omega g squared plus omega k squared. So this is my second eigenvalue. And omega k minus omega squared m becomes, here I subtract this, and I get 0. So my negative omega k's are not impacted. Here I get omega k squared, negative omega k squared, negative omega k squared, 0, 0, 0. And I'm going to multiply this by A1, A2, A3. Just like before, this is all equal to 0. I can factor out, when I say this is equal to 0, I really mean that it's equal to a 0 vector. So each of the components individually is equal to 0. So here I get A1 equals 0, and let's see. Yes, I get A1 equals, no, I get A2 equals 0. From the first equation and the last equation, A2 equals 0. And then if A2 equals 0, I get A1 equals negative A3. So I'm going to choose A equals negative 1, 0, 1. Could have chosen the positive to be the first one. It doesn't really matter. So this is the middle pendulum stays still, and these guys do this, and they oscillate with an angular frequency of the effect of gravity plus the effect of the spring. Now I can consider my last one. This is a little more interesting. When you see what these modes actually do, it does make physical sense, doesn't it? So omega g squared plus 3 omega k squared. In fact, if you've done enough of these problems, you maybe sort of start to see, well, I'm probably going to have some mode where they all move together and they have the frequency that they would have without the spring. I'm going to have some, and then I'm going to have modes where they either move together or opposite each other. All right, so now my k minus omega squared is, this gets a little gnarly. I have a negative 2 omega k squared. My off-diagonal negative omega k squareds are not impacted. Here I have a negative omega k squared, 0, negative omega k squared, negative omega k squared, 0, and then here I had better have the same thing I had there, negative 2 omega k squared. All times A1, A2, A3. Let me just write this as a vector because you guys have not been, you might be a little uncomfortable with my slightly sloppy notation. All right, so then here I get from this top equation 2A1 equals negative A2. From my bottom equation, I get A2 equals negative 2A3. And this equation is going to be the sum of those two. So I will be lazy and not bother. I get A, and then I have to choose. I'm going to choose A1 equals 1. That makes A2 negative 2. And then if A2 is -2, A3 is 1. So that means that when these guys, the two outer pendulums move this way, the inner pendulum moves that way with twice the amplitude. Let's see if I can do this. Sort of like that. So then we can write out the general solution. All right, so we can put this all together, and phi1, phi2, phi3 equals some overall constant, which we will call A1, cosine omega g t minus delta 1 times 1, 1, 1 plus A2 cosine, and then our omega is the square root of omega g squared plus omega k squared, square root times t minus delta 2 times 1, 0, -1 plus A3. Then our third cosine of our third omega is the square root of omega g squared plus 3 omega k squared, square root t minus some third phase shift times 1, -2, 1. So, in general, your motion will be the sum of all of these three different modes combined. Woo! Like this, and like this, and like this. So previously we had found that for two coupled oscillators, if we use the variables C1, which is the average of the displacement of the two coupled oscillators, and C2, apologies to those of you who actually know, who are Greek, because I'm butchering these letters, and actually I always write C is more or less a squiggle. There is actually that's not even a good job. There is a form for it, but my C's are squiggles. So if we use these two variables, then in fact we find that the solution is neat, because the matrix, the two matrices, the mass matrix and the spring constant matrix, end up diagonal. So we had the two equations, mx1 double prime equals -2k 1 plus k2 times k1 x1 plus k2 x2 2 double dot equals k1 x1 minus 2k x2. This is for equal mass, equal springs. If we then do this substitution, we can write C1 double dot is 1/2 x1 double dot plus x2 double dot. C2 double dot is 1. These are really bad C's, I'm sorry, but I think that you can follow. And then we can solve this. If this turns into add these two equations together, and you get MC1 double dot equals, now here I have negative x1, I'm left with a negative k1 x1 minus k2 x2, so I am left with MC1 double dot equals negative k c1, and here take the difference of the two equations and I get m, and here I'm multiplying through by 2, multiplying through by 1/2, MC1 double dot, and then here this minus that, I get a negative 3k x1 minus x2, which gives me a C2. So these two equations are then decoupled if I choose to use these coordinates, which happen to correlate with what we had for the eigenvectors for this system. In this case, my new mass matrix is M0, 0M, and my new spring constant matrix is K0, 0, 3K. The system is totally decoupled. So when we worked with X, we had the eigenvectors 1, 1, and 1, negative 1. These eigenvectors form a complete set, which means that I can take an arbitrary vector. Let me call it, I will draw a picture of Bob. So I will take an arbitrary vector Bob, and I can write it as, let me not use A's, and let me use an alpha A1 plus beta A2. I can write any vector as the sum of these two vectors with some constants out in front. And that means, so when I take an arbitrary system, I will always, my eigenvectors will always form a complete set. I can always write any displacement as the sums of those vectors, and I can then choose to use coordinates such that my matrices are diagonal if I am choosing coordinates where, in this case, C1 is x1 plus x2, C2 is x1 minus x2. This corresponds to rotating the coordinate system if these were positions, rotating the coordinate system so that it lines up with the eigenvalues. So then I can consider the general case. I should mention this set of coordinates, using coordinates like this where they are special, these are called normal coordinates, and they are the coordinates for which the matrix equation, the matrices in the matrix equation are diagonal. So in a general case, we can write some vector Q, and for the ith component, the ith order oscillation is cosine omega I t minus delta I for the ith solution. This is the eigenvector. This is the eigenvalue. These are, in general, independent, real, and complete. So any vector Q can be written as the sum over all I of those normal coordinates times the eigenvectors, the ith eigenvector. So to show that this works, we will take our equation look at the ith eigenvector. This is the equation we want to, that we are trying to show works. So we have we are going to then, so this solution, this is our i's are defined by being the solution to this equation with a plus, and then we are going to plug them into m q double dot equals negative k q. We will use this form, which means that q dot, the a's are constant, is the sum from I equals 1 to n of the derivative of this expression, except this is constant, this is not, so we only have to take the derivative of the c term. And then we want the second derivative, and that just means adding another dot. So we will look at m q double dot. This is m times this I move this in here, I act on that, and I can get then when I act on this, because the m, so here, this is going to give me m c double dot a sub I, but this is just a negative k. Yes, this should have had a negative. My notes had a mistake. This gives me a negative k a times c sub I, and this is just negative c sub I omega squared m a sub I. So this is solved if this is true. C sub I double dot is negative omega 1 omega I squared c sub I.